Good morning, y'all. Hi everyone. I'm Dia Brown. I'm under the advisement of Dr. Juan Pablo Gévedon. I'm a PhD student in the Department of Architectural Engineering at the Pennsylvania State University. And I'm going to be talking to y'all today about a topic that is very near and dear to my heart. I spend a lot of time with these materials, and that is transforming agricultural residues into high-performance SCMs using high-energy ball milling. And so to kind of, maybe this works. Maybe not.
Just click on the screen here.
Oh, big sad. Okay.
Yeah.
Cool. So I will stay over here then. Okay. Let's see. Oh, there we go. Wow. Now we get to see that twice. Fun. Okay, so to ground us into this conversation, I kind of want to give like a brief introduction. I'm sure a lot of y'all folks know about this kind of stuff, but like it's good to just kind of remind ourselves of why we're using these other materials in the first place. So in terms of why use less cement, according to the IEA, we have about 37 gigatons of CO2 emissions a year globally, which is about 6 billion elephants according to the World Wildlife Foundation, if you do some back of the envelope math there. So we would like to reduce the amount of CO2 that we're putting into our atmosphere. And then when considering that cement is the third largest source of human-made CO2, that seems like a pretty good spot for us to really make a difference. And so then why use supplementary cementitious materials? Well, of course, sustainability. We would like to have a planet for ourselves and for our next generation. But it's also important to remember that there's other factors at play. Supplementary cementitious materials can improve the strength. It can also improve cost. You can get more locally sourced materials, and that can change your cost. There's also other amazing studies that look at alkali-silica reaction mitigation, or other durability concerns that you may have that an SCM can potentially help with. And so now why looking particularly at cereal crops as SCMs? They're abundant in the global north and in the global south. So I also do work with corn, stover, and wheat straw. There's a lot of that in the US, but there's also rice in the US and also in the global south. And so all of these cereal crops are in the realm of grasses. And the thing with grasses is they produce opophytoliths, which is the kind of the rigid structure that's in grass that prevents it from, it's trying to resist herbivores, which is great for the plant while it's around to try to resist herbivores, but it's also great for us because opophytoliths are that very amorphous siliceous material, which is great as a source of silica. So, rice hull ash can be a great SCM, but it can have a lot of challenges in its physical and chemical properties. And so the question is, how do we improve that physical and chemical property for incorporation into cement? And a kind of brief intro to that picture there is, it's kind of hard to see, but at the top right, it kind of shows like the dehulling process for rice. So just kind of a reminder that like we have a big historical context for our use of rice, and it's a great choice as an SCM. And so the hypothesis is that by doing some wet milling process via attrition milling, that you can modify the ash and make it more viable as a partial cement replacement. And so the RHA that I have is from an energy plant, and so that is another way of using rice hulls that are left after the dehulling process for commercial rice. It can end up in an energy plant and be used as energy, but then the next question is, what do you do with that ash from the energy plant? So we took that ash and we characterized it for as received and also from attrition milling. And so these are the milling conditions that I'm working with, and as you can see here on the left, we have what our attrition mill looks like. And so I'm milling it at about 400 RPM with a 5-to-1 liquid to solid ratio. So there's a 5-to-1 ratio of the material to, or the water to the material. And then also a 10-to-1 ball to powder ratio for about 3 hours. And so the kind of categories that I have here is as received rice hull ash, so the rice hull ash from the energy plant, the attrition milled, which I'll be referring to as MRHA, and then also I did work with some milled RHA with in situ CO2 bubbling, which is another feature that we have on our attrition mill, is the ability to kind of flow different gases into the mill while it's running. And so the RHA, the MRHA, and the CRHA were tested for their reactivity and their compressive strength. And as you can see there on the left, there's one of the amazing undergraduate students who works in our lab doing some isothermal calorimetry for the R3 reactivity test. And then on the right there is kind of what one of the cubes after putting the milled rice hull ash ends up looking like. And so what we found is there's that substantial jump in the strength and reactivity after attrition milling. As you can see there, there's that doubling in the reactivity from doing the R3 reactivity test. And then when looking at the compressive strength, there's a tripling and a quadrupling of strength in comparison to the untreated material. But there's only minimal changes in the phases present from the XRD. And then I also ended up looking at the 29 silica nuclear magnetic resonance just to see if there's any change in the coordination of the silica, which there doesn't appear to be much of, but this is something that I'm still exploring a bit further because there's a whole different side of things for NMR to kind of look at what the coordination is, and I have some future work related to that. But the surface area nearly doubles after that milling process, and so that is something that's very encouraging. We also have a shift in the particle size distribution, so that allows for a better incorporation into the cement mix. But another big thing is by doing wet milling as opposed to dry milling, you're also able to do a leaching process. And so something that is amazing for plants is potassium. They need potassium to grow. But the big issue is we don't want a lot of potassium in our cement. We don't want, potassium-rich cement. That's not great. So by doing this wet milling process, you actually have a pretty substantial decrease in the potassium level. And something that I'm exploring further right now as well is the fact that rice, when you're getting it from wherever, depending on the season that it's grown, depending on the location that it's grown, depending on also how it is burned at the energy plant, because when you're getting it from the energy plant, you don't have the luxury of kind of changing the conditions in which it's being burned. It's just being burned for energy and that's it. The hope here is that this can also kind of homogenize the chemistry of the material by that milling process. The only note that I will say, which I did not highlight here as much, but is that there can be potential for contamination depending on your mill type, and so that's another factor to consider is like which ball media you're using, which ours is corundum, which might be explaining why there's a bit of an increase in the alumina, and as well as we have a steel mill, which can explain some of that potential contamination. So to conclude, so the attrition milling technology is a viable solution and addressed some of these questions of how do we kind of better incorporate rice hull ash into cement. And something that I did not note earlier is that the cubes that I made, I didn't end up using any admixtures for, and I did about a 30% weight replacement of the material with rice hull ash. And so the workability is something that I'm going to be further exploring, but it substantially improved as well. And so some of these key conclusions is that the reactivity does increase after this milling process, so does the surface area, and the potassium content is reduced, which can potentially reduce unwanted phases in later ages, which I'm currently waiting for those cubes for, but can also influence early hydration as shown in previous works. Something that I am looking at more is kind of that homogenizing effect potentially from other rice hulls, but also looking at the workability of the material and kind of getting a more quantitative conclusion on that because it is definitely substantially more workable after that milling process. But yeah, that is it from me. So if y'all have any questions, I welcome them.